session of our workshop today. Our last speaker is Mr. Sumit Misra, who is the General Manager of RS Software. Sumit holds a master's degree in Electronics and Telecommunication Engineering. At RS Software, Mr. Misra has strengthened and extended the position of the company in payments industry by managing the RS School of Payments and the RS Payments Lab, enhancing the domain expertise by instituting best practices in knowledge management. During a professional career that spans over 25 years, Sumit has helped leading companies in the payment industry determine technical strategies to build competencies that best fit the needs of their customers. Today, Mr. Misra is going to talk on data stream analytics.
Thank you and good afternoon. I know it's the last session. Everybody is probably looking for things to get over and go home. But I'll try to make it as interesting as possible. And here we have some industry information and some preliminaries on how a data stream works. So we'll talk about the business need, then the modelings and the mining things, techniques that we use, a concept of standing queries, and then a conclusion. So first, the business need. So we today know that there are so many applications that are in the cloud, viral things are happening, Facebook, Twitter, Google, whatnot. And if you see the architecture, it is the application that is in the cloud being accessed by multiple devices through browser, tab, mobile apps. And here is your billions of users who are accessing and generating information or data. So what it is doing is it's generating a very large set of data. And if we take Facebook as an example, it has about 1.32 billion active Facebook users per day, every day. And they are generating 4 million likes per minute. So if you have to do some opinion or advertisement or anything based on such the likes of the person who are using it, you have to be pretty fast using that and giving responses. And probably whoever is using Facebook sees contextual advertisements in the right middle column of the system. Second example is UPI. Why I brought it? Because of two reasons. One is this is made in India, and it is next to Facebook. This has the adoption rate highest in the world. And the third reason, which is probably close to my heart, is this application was developed by RS Software. So, thanks. So this is, if you see, the volume has just uptaken, and it is going to the level of, as I speak, it is 190 million transactions per month, and it is clocking at the rate of almost 30,000 crores of rupees per month. So why I want to say this is that it is an imperative that it works right, and it works right every time, otherwise there's a business impact to somebody. Today using an UPI, you can send 200 rupees, 2000 rupees, and today if you calculate the average ticket size, which is amount that is transacted through UPI, it is about $21. Now this is soon going to rise as Tez and WhatsApp, which will release maybe in couple of weeks, they start providing UPI based transactions on their platform. And there is a high possibility that Singapore will start using this application, and they will allow money transfer using UPI on this. So bottom line is that this is a very adopted system, and we are going to do a lot of money transactions through this platform. And every money transaction is a stream that gets generated. So if we look at the complexity of these systems, we can In the analytics, we know that there is a descriptive analytics, which is at the lowest, where we can describe the data using analytics techniques. Then there's a predictive, where we use regressions, linear regressions and logistic regressions to predict, to classify things. And there's a prescriptive, which is very complex, and you can almost predict and say, you know, you ought to do this so that it doesn't happen or does happen, whatever. Here is, if we see that the data stream that is trying to handle the right column of the entire story, which is all high, medium, super high type of complexities. And just to set the context what this entails, there are certain examples that I will give here. And if you look at the prescriptive online, which is the red one at the top, this is Google predicts the query string and provides alternatives. That is, as you type, it does worldwide. So that is the highest complexity in this, in a stream processing environment. And then in the lowest, you can see that what items are brought together, like it is doing that. So this is just trying to give you a context of where we are trying to talk about data stream analytics. We have heard a lot of analytics by now. So if we look at the descriptive online, where the fraud detection of e-commerce purchase, that is very pertinent. And it is always a concern of the e-commerce guy that I'll not get paid. Something will happen and I'm not going to get paid. So they have to track and understand whether a transaction is suspected to be a fraud almost in real time, because then they will not allow, or they will say it will take so many days, or they will do something so that to do much more checking before they ship, the Flipkart ships you the goods, or say I accept the order. So that is the thing that is done by the Amazons of the world and Flipkarts of the world. So this defines an area where the data stream analytics is being used. Interesting questions that Google as a company starts asking themselves is, how many new users have logged in since last month? So you can understand that Google cannot keep the entire list of people that is logging in every minute, every day. It will be impossible to keep that. But still they want to answer how many new users have come this month. This is a non-trivial problem. If it had been 100 users, you could have counted, and it's a very simple exercise. But if it is a billions of users, it's a very complex task. Uber, what should be the dynamic price that would not put off customers? They try to do that. Right now we are facing surge prices which are abnormals, but their algorithms attempt to give a price which is reasonable. So that is again a data stream. They're doing it in real time, analyzing the streams. So that is the context. That is why this is a business context we talked about. Now let's talk about the models and the mining. So what we will do is, like in the morning when Bimalda was talking, he said that we learnt about the multiplication of two numbers and then we extrapolated that, and today we can do so many things. So we are trying to address a very simple 2-3 techniques or algorithms which we'll try to see how it happens, and probably in future you will use that as an extrapolated manner for handling different problems or very complex problems using this simple algorithm techniques. So that is the intent of this next whatever 10 to 20 minutes, 25 minutes that we have. Okay, so the constraint that we have in data stream analytics is we cannot store all the data from the past. So when Professor Chandan Mukherjee was talking, he also mentioned this. The stream objects can be scanned only once because you cannot store, it just flashes by, that's it. You have only one chance to look at it, do whatever you want to do, and then that's gone. Usually we need to answer it in seconds. When the query comes, we want to answer it in seconds, or almost in real time when Google gives you that options. But the general approach is an approximate answer will do. You need not give an exact answer. That's a blessing that you have for this. So to handle all of these, this is the standard stream model that is used. Very simple. There is an input stream. You can see the time going other way because the recent one is very near so it is somewhere near this one. So these are the near times. These are the old times. So here is your box. This is a stream processor. And you have standing queries. Standing queries means you want to have answers to these queries. You have the questions upfront ready. It is not ad hoc. You want to have the answers, how many new users are logging in. So that's a standard question that you have punched in somewhere and it is kept there. And the system will need to answer that question anytime, every time. And there's ad hoc queries. The problem is with ad hoc queries, because we'll come to that, why it is very difficult to answer ad hoc queries and how to handle that. And then you have the output stream. And if you look below, there are two boxes. One is that archival, all the transactions are stored somewhere in that big database or whatever. But there is a small working storage area, which again Bimallah said that we have something here like the tables. So this is the working storage area that we have here. Even it is terabyte level, it is still finite. It is not infinite. Stream is infinite. Storage, finite. How to handle? All algorithms will be trying to juggle with this entire restriction in the resources. So example of ad hoc queries, how many new logins in the past week, month. Now these are different time stamps and you have to be able to answer that. Standing query, what is the highest number so far? So you just keep one random variable, you populate with the largest number that you see, you can answer that. That's a standing query that is there. Ad hoc query, you have to do something interesting so that you can keep answering those queries. Any questions with this? Right. So now let's see mining. What do we mine for? We can mine for multiple things. One is mining for classification. That means that stream is going up and it is from 6 a.m. to 2 p.m. we are trying to get how many were the good transaction and how many were the frauds. That's one. Then after a while you want to get another set. After another while you want to get another set. So if you see, does it look same? It definitely it changes. So if you look at the underneath that entire system, as if there is a model which generates this. You cannot see it, it's like a conceptual thing, but it is not uniform, it is changing. It changes with time. So we call it in our terms drift, but let's forget about the technical terms. That means whatever the data that gets generated doesn't have the same pattern all the time. So it's changing pattern and that is acceptable. So in this morning part and in the afternoon part and the morning part you have large transactions. But when after 10 p.m. obviously people go to sleep and the transactions are less. In whatever the example that we have taken. It is just the reverse if it is an e-commerce transaction. People go home and start buying things. Similarly, you mine for frequent item sets. What are the things that are bought together or that are observed together? It could be that people are doing medical tests. So if I am a big conglomerate of doing medical tests, like some lab, ABC lab, and I'm getting the data, what are the tests people are coming and doing the tests for? I will see, okay, it's a blood test and what is the test for? It is TCDC, hemoglobin, maybe liver function test. So if I see a liver function test, then along with that there will be a lipid profile. So does lipid profile and liver function test go together? Or is it that I am seeing them being that tests are coming together? Is some disease that is going on? Some doctors are prescribing always this together for whatever, last 15 days? So those type of questions to be answered, we do mining for frequent item sets. These are the frequent item sets. And so here is a frequent item like A, G, W are the three tests, let us say, and you see AG together, GW together, AGW altogether, and this is the count of how many such tests have happened. You will always see that A will occur, whatever the number in the A, that will be definitely more than AGW if it is together, because they are called singletons. They will occur more than doubletons, and doubletons will occur more than the tripletons, and so on. So this is again a frequent item set, and if you see with time, this is occurring separately. Now if you see the last one, it is interesting. It is actually only AGW is the test that has occurred. No other test is occurring, and because that is one, all of these are ones. So this gives a picture of a changing pattern, and what is it that I am mining for. These are the two things that I am trying to picture. The third thing that we do is clusters. In the cluster you will see that there are, I think the separation has got a little weird because I did in PPT and this is Linux system. So it actually shows that that got overlapped. The circles are actually below and the other one is at the top. Anyway, so if you see here, now this is all gone vary because of the picture. So see this blue, this is an outlier because you see that this blue is well apart from these blues. So what is happening is, so this is an outlier, this one is outlier, and this small circle is an outlier. But as we go, I'll just do all these three. Then this blue does not remain an outlier because there is a change in the clustering of the entire thing, and this blue gobbles up that small one, and this blue invades into that other territory when the red reduces. So this again is a clustering phenomena, and clusters we do to typically find out outliers. So when we talk about streams, there is a clustering going on, the cluster keeps on changing. There's an outlier that I detected, the outlier starts changing. So any answer that I gave 4 hours back may not hold true after 4 hours. So these are the three types of generally applied things. One is clustering we saw, then we saw the frequent item, and the first one. Now to treat the windows, there are two types of time windows that we treat. One is called the landmark. That means each set is like separate. I have seen window 1, I'll see window 2 and window 3. They are non-overlapping in time. That's landmark. And the sliding window, these windows keep rolling over. So if you have any results coming out of that, you have to be cognizant that I'm overlapping 25%. So past 25% information is getting overlapped. So how do I treat that when I finally give my answers to the queries that comes? So in the landmark, if we see, here are certain counts, mean, standard deviation that is there. Again, this count is increased and the mean has changed and the standard deviation has pretty much reduced. So this set, if you look carefully, this is a much sharper set. Everything is more closer to the mean, standard deviation is low. And once we go there, here it is quite flat because things got dispersed. So this is the distribution pattern changes along with the time. So when we are working on the answering things or building software, answering business problems, these are all the things that can happen, and we have to be prepared for that in our software. So this is the data set that is going on. This is the stream. These dots and dashes are the streams, various streams. So for example, you are trying to find out how much sale of commodity is happening in a retail store. So these are called synopses. So what is this doing? It is trying to model this thousands and millions of data that is crossing the window into a few numbers which will probably represent that window data. This is called the synopsis. And you can keep some of the synopsis. You can select some of the synopsis, all of these. You may not keep all of them. You can do a sampling of the synopsis and keep them. All of these are possible. But what happens if there's a sudden rise in data? Your entire system is built to handle whatever, so many, everything is finite. There is a boundary of operation that you can build on. It may be large, but still there is a boundary. So if you have a very large amount of data suddenly coming in, you have to reduce the load and you have to degrade gracefully. You have to degrade the service because you don't have infinite data, infinite memory. So how do you degrade gracefully? This is where sampling comes in. You do not consider all the windows. We do not, you skip windows or you skip whatever, you skip things. Now, what is the strategy that one needs to take in order to do this? So, what is the strategy that you would want to take in order to do this? So, I'll give an example here. So, suppose you can, POS is point of sale. That means where you swipe your card, and it's a retail store where you swipe your card and you purchase things. So, how do you sample if you can store only 1/10 of the POS data that is coming? Now, here the interesting thing is that if somebody says this, standard way of answering is whatever items are getting purchased, I will do all of these typically have a item code. I will hash the code and try to map it into a number from 0 to 9. And if it is say number 3, I will keep, rest I will throw. So I have only 1/10 of the data that I'll be able to keep. That's the standard way. Now, will that work for every situation? No, because if my standing query is, or if my ad hoc query is, if I want to process, if the question is, if I want to find out purchases that contain item A, that's my problem statement that I'm trying to solve. So if I do that 1/10 by using a hash and picking any number and putting it, just selecting 1 out of 10, all the transaction that I'm seeing coming through, I'll probably get a answer right if the distribution is almost similar in each of the basket of each of those customers. But if my question is want to process purchases by users that contain 2 or more items in A, then sampling at 1/10 rate normally will not give me the result, because it is very unlikely that I will be sampling exactly 2 A's side by side, one after the other. So that is the reason I cannot do that. Then I have to change the strategy. Instead of sampling items that I see, I will start sampling customers that I see or the baskets that I see. So I'll pick one basket out of every 10 or one customer out of every 10 instead of picking one item every 10 items. So why I show this is that the way that you want to reduce the load and do the sampling will depend on what is it that you are trying to answer as a business problem. That is the purpose of this. Any questions with this one?
Is it a market basket?
It's not a market basket, means associations. This is not associations. It is just sampling in the basket. Okay. And for reducing the load, now this is the second question. What if the rate of arrival increase and you cannot keep 1/10 even? Then you have to find a strategy so that the difference between the probability of actual errors and probability of actual fractions and the estimated fraction, that the probability is greater than a relative error is bound by some error bound. So how do you do that? I want to obviously have a lesser sample taking from the data stream, because now I have larger bursts of data or whatever the reason may be. But I'll try to minimize the error and keep it under a error bound. That means I'm guaranteeing that it will not be more than this. So that means I'm degrading gracefully. I'm degrading my service. My errors are increasing, I know, but I know that right now my error will not be more than 17%. Then some more problem comes in, then I say, okay, I change this. Now it will not be more than 23%. So I'm degrading gracefully. That's the message I want to give. And here we utilize something called Hoevling inequality. I will just give you a glimpse of that. I'll not go through the maths. Oh, I cannot go through because it is good. So I cannot even give you the glimpse. You can read it somewhere else. Yeah. This is unreadable. Okay. Reliability is low. Okay. So if you see the research and the innovations where it's happening in this it is happening in finding innovative synopsis data structures for like the list, trees, graphs, and all of these, so that it is optimized for latency of search, so that your search is faster. Your time complexity of update, because you have to, whenever there's a synopsis data, you have to update once every time a stream comes. So you have to be it has to happen fast again, the time complexity. And the space complexity of storage has to be small. So you are bound by all three sides of the triangle, and you have to function that way. So all the research that that is being done right now is trying to optimize all of these. So let us see how a spam filter works. Everyone gets some spam and very annoyed that, okay, they cannot catch this spam, it has come here, it's all of that. But if you want to know that how much spam is filtered, it is actually in the range of, here it is written 80, but it is now crossed 88 to 92% spams are filtered. So you are not hit by a bus, you are hit by a small rickshaw or something, and you are annoyed. So how it is done? So what they do is, you have, first of all, you need to know that somebody reports that is a spam. The moment you do that, that email address is hashed. And you have that I told about the local storage that we keep like in the back of our mind, and there's a local storage there. So there are, suppose, 1 GB of memory. So basically 8 billion bits are there. So you take the address, you hash it, and you get an address which is below a 8 billion number. And if you see that, you go and mark a 1 or a 0 in that, say let's mark it as 1, rest as 0, we mark a 1 in that bit. And whenever a new mail comes, that is also hashed, and people see that whether there's a 1 in there, and they figure out that, okay, that is a spam, and we'll remove it. Now if you do this, for this example of 20 bytes of data, 1 GB of RAM, 8 billion bits, this technique is Bloom filter, 1970, it was discovered. So if you see all these maths, they are discovered even maybe 200 years ago, which are being applied now. So these are not new things. We are applying things. This is not that old, but we have other central limit theorems and all of these. They are really, really old. So we see De Moivre's name there. We see even very old names. So if you do this of technique, you will see that it is only 11.75% correct, accurate. So it is only 11.75% accurate. Now if you twist a bit and you use 2 hash functions. So when an email ID comes, you hash it and see if there will be 2 IDs that goes into that 8 billion bits, and you mark both of them as 1. Now you get again an address that comes, you again hash with 2 numbers and see if both the bits are 1, then that is definitely a spam one. If you do this, you reduce the false positive error to 4.89%. There are maths behind it and all. But you see, when a stream comes, you just see the address, apply 2 hash functions, look at a bit, and you are answering. It is pretty fast. So somebody has devised this in a way that you can answer very fast, you can update it, all of that constraint that we talked about are met. The intuition here, we can talk about the market basket you are talking about. We can use similar techniques to figure out if 3, 2, whatever items are occurring together. Similar hashing techniques can be used. I'm not going into the details of that. So this is a classification or filtering mechanism that can be applied. Any questions on this one, spam filters? Yeah.
Is there any threshold, suppose how many number of times a people should spam it or not? Because one person may make it a spam, but another person is not making a spam. So is there kind of threshold?
You are talking about the acquisition of the data verification. So that is not part of this. We have a, once somebody verifies and gives that this is an error, then we mark it. So it can be, the threshold can be set once this is reported 7 times, we'll take it. That's outside the solution problem of this. That's a business decision that has to be taken. Yeah, sure. Right? So let's go to the next one, which is frequent recent items. Now that recent is very important. So there are many examples, like when you go, depending on the season or time of the year or whatever, you buy 2, 3 things together. So that doesn't happen. So you do not keep on buying cold drinks maybe in the winter, or ice creams are not bought in the winter. So those things, you will see that's seasonal, it changes. So but the recent has a problem. Recent means, what do you call by a recent? Recent means how much is the period of time. So for a large universal set N, you want to find out top 5 most frequent recent items. Example, let's say Swiggy orders. Swiggy is trying to figure out what are the things people order from nowadays from, say, Arsalan. So you will see things have changed in the recent past. So, or the Uber Eats or that requests, so that is different. TV channels being viewed, that is a TPR, huge money out there. All these set-top boxes try to do that mining. What are the things people are seeing? When? That Z or Star or whatever, which particular program, one after the other, all those sequences. So how is this problem solved? This business problem is well understood. But the problem is how it is solved. So what we do is, we keep a set of buckets. Each have counters, so we count them. There are only counters that is there. So every time we encounter that something has come, there is some counter out there. So first of all, we reduce the counter value by the elapsed time. So suppose elapsed time is 10 days, or days is too much, maybe 5 days have passed. So you take a number between 0 to 1, put that 5 days on as a power to that, and multiply that with whatever the count that is there. So that is going to reduce, because less than 1 to the power and multiply, that's going to exponential functions reduce, and then you add a 1 because a new thing has come. So this is called exponential handling of the counters, and if you do that, then all these buckets, you see that gets changed. So if I keep items, hash them and keep it this way, and then I filter the top 5, then I can say that these are the 5 recent items that are being bought together. There are a lot of difficulty in doing that, because I'll not go into the difficulties, because then it becomes a little more complex. I'll just give a hint of that it can be that A and B has come, A and C has come, but A, B, C has come, but B and C has not come together. But typically the algorithms are built in a way, it is called closed, the maths term is closed. Yeah, but B and C in itself has not come. Without A. It has not come. But all these algorithms typically gyrate to the solution that will be an error we have to live with, because you can understand they will try to do a closed set type of solution.
Transitive property. A, C and C.
No. It's a little different. But the issue is that I'm not going to the difficulty part of it. Let's say that it is difficult to count because suppose an item set has come with say 5 items, and there are about suppose 20,000 items that can be bought from that store. So you are maintaining some counters. Now when you see 5 items, what is that? And you are maintaining the frequent items that has come. So the combinations become 2 to the power of 5. So the combinations 2 to the power of 5 is the lowest one, then you can even more, others are higher. So it generates a high combinatorial explosions are there if this larger number of combined things come, and counting that, maintaining that, then there are other algorithms to handle that. But very simply, these are recent items. I'm not talking about item sets. I'm talking of items now. If it is only the items, this algorithm that we have shown is good. But then, will you count all the 20,000 buckets and 20,000 items? No. Every so often, what we'll do is, we'll do some trick. So if you take this and if you see just the lower part, which is the matrix. So here the latency of search will be in the order of 1. Time complexity of update will be order of window size, that means how many things come, plus n log n, because you will be searching binary search or something, so that is going to do that. But you can reduce that n of that n log n by using something called pruning. So you don't keep everything. You just keep over x, whatever that threshold, and the moment you do that, your n log n comes down. So I am not trying to solve all the problems. I am giving you indicators which are used in order to do this. Again, so again the space complexity reduces from order of n to that number order of threshold. Right? So any questions with this? Frequent items? We are moving streams, right? Yeah. Oh, the pruning is that you take the sets that are there. And suppose I tell you that you cannot keep more than 100 sets. You have 20,000 items. So the moment you see that a new item has come, what will you do? You look at all your things. The lowest one, because you are degrading with exponentially, some numbers have come to 0.002. You say drop that out and put this 1, because this will be 1. Right? So if you keep these things in a ad hoc query, if I say that instead of 5, tell me the top 10 items, you can still answer. But if I say, tell me the top 101 items, you cannot, because you have only factored in 100. So this balance act is there. That's the only thing I'm trying to say. Now this is very interesting. We will use the examples, we'll not derive or tell about the algorithms. So this is, we are trying to measure the uniformity of data. I am getting lots of data. Say suppose people purchasing from a petrol pump, or this example is integer, so I cannot say that. Suppose they buy only liters of petrol, you cannot have decimals. I'm just giving an example. So there's a stream of data coming that, whatever that numbers are. You want to understand whether they are very diverse. So in other terms, is the standard deviation very high or not? That's what is in your mind going on. You cannot do the standard deviation so easily in this environment. So you are trying to find out what is the uniformity of the data. Now there's a concept of moments. That means you see that various numbers here and you see the frequencies, and if you raise the frequencies to the power, that is called the moment. So the 0th moment is how many distinct values that you have. So here you have 1, 2, 3 and 4. That are the 4 numbers. So if you see 4 and you power it to 0, it will become 1. So all the frequencies to the power of 0, if you add, it will actually be the different distinct items that you have. If you raise it to 1, you will have what is the length of the stream that you have seen. If you raise it to the power of 2, you come up with something called a surprise number. And this surprise number is a measure of the dispersion. 2 minutes. Okay. So, and there's a way to say that if it is evenly spread, it will be smaller number, and if it is unevenly spread, it will be large number. That can be, we can arrive at that. And then I'll talk about the standing queries. So what we are trying to do, we want to find out the distinct items that are there we are crossing. Or I want to count the number of ones I have seen in the last n bits. One can be one, or it can be presence of something or absence of something. And the second order moment. Second order moment, I just showed that why it is required. We are trying to find the dispersion. I don't think I can cover all of that because of time constraint. Let's see how much we can cover. So here are the distinct items, and you can see that picture that gives the distinct item. So in the distinct item, so here is your, this again that stream. Now I'll give you a magic algorithm. What you do is, you have a hash function which is like this. So if you apply the hash function to this is what it comes. You have to believe me, don't compute. And then you convert it into binary, and then just put the number of trailing zeros that you have, last zeros. For example, if it is 4, that is 100 binary, so you have 2. So you have put there, these are the trailing zeros. And if you put a maximum of this, you get a number, which is 2. And if you raise 2 to the power of that r, you get 4. Now this is a complete mumbo jumbo, right? But this 4 is very close to the number of distinct items that you are seeing. You don't have to believe it. It is called, in 1983, FMA algorithm, Flageolet-Martin algorithm. But interesting thing is, this is again, as you see the stream, you can do it. So you can find out the number of distinct items looking at this. Don't have to copy this. If you get the reference, you can see the slides can be shared. This is a Stanford University press book from which I have copied, so you can take that. That's freely available. So I'm just showing that there's an algorithm to do that. That's it. Similarly, you want to find out somebody is doing a ones and somebody is doing a click and a 1 or a 0 for there's a long stream of, they want to come up with how many people are in the age group of 18 to 28 that are in the line or something, trying to do some analysis. So counting ones in a window, that is the problem statement. So here what they do is, they try to bucket it in 2's multiple. That is, it is 2 to the power of 0. There are 2 to the power of 0, then there is a 1, the 2 to the power of 1s, then 2 to the power of 2s, and all of that. Window buckets. And then you can record the starting of those windows, and you take this window as far as you cover the number of bits that you want to be there. So for example, here I want to cover 4 bits because 2 to the power of 2 window. So from 55 I start till I cover 4 bits. It's not a 4 bits, it is a 4 ones that I'm trying to count. So if you can bucket this, it is very simple to bucket this, because then you have, this is the only number that you're keeping, 62 ones, this is the number that you're keeping, this buckets, you can see this. And then if I ask you, estimate the number of ones in the last 10 bits, what I'll do is, I'll try to cover this. You will take the first 10 bits, means you see there are 4 buckets. You can find out that it will be 4 buckets. You take 1, 1, 2, and half of the last one. That is the algorithm. So actual number of exact count is 5, but you will arrive at 6. Again, this is a DGIM algorithm, 15 pages of proof, but it proves that this works. But you need to know, as an engineer, I need to know it works. That's it. This 2002, it was published. It is there. Estimating moments, I'm not going to, this is little difficult to explain. That's the reason I'm not covering. This is again a Alam Matthias Slezy algorithm, that is the AMZ algorithm. And how it is mapped for doing the moments for a stream, that is also there. Okay, I'm skipping that. Almost at the end. So basically what we are trying to do is we are trying to find needle in the haystack with perseverance. But there's a limit to your accuracy. Again, it's all garbled, unfortunate. Yeah, so basically I'm saying that suppose there are n number of items, the probability of finding something is 1 by n. Probability of not finding it is 1 minus 1 by n. If I repeat it n times and n is very large, then I have 1 minus 1 by n to the power of n. Limit n tends to infinity, it will be e to the power of minus 1. So probability of missing is 36%, probability of 36.8%, probability of finding is 1 minus of this. So even if you try infinite times, you will not be able to reach that reliability beyond this. So there has to be some stronger methods of arriving at a better answer. So these are all gone. So conclusion, mining data sets have moved from research to application. Single scan is important. We have shown you some tools of distinct item and all of that. And this can be a very important tool set to think and research on the beyond things that is coming. And this remains still an active area of research, and it is really fast progressing. I'll take the questions later. I'll just give one example where it was used. Stream was used in the socially important example. So it was that is gone, whatever. So 2014, WHO reported that after 29 deaths that Ebola virus is deadly. And then a stream analytics of call records. You also heard about call records in today's. Stream analytics of call records tried to figure out from where the point of origination, if somebody has moved within 14 days in other areas of Africa or anywhere else. With this, they were trying to quarantine and get the information regarding contain the spread of the virus, Ebola virus. And this was done using stream analytics, and it was quite effective. And this movement part was emphasized because in entire Africa, even if you do not have a bank account, you still have a mobile phone. So they use that as the important information in order to contain the Ebola virus. So that was the application of data stream analytics in society. Thanks. Any questions? Yeah. Yes. Extent buckets. Yes, that is right. Main issue. That is right. Yes. I've already shared the slides. Yeah, I have shared in if you can do a PDF format of the PPT, that will be, you'll get a better quality. Okay. Yes.
Has the stream processing been applied to, let's say, high frequency trading data?
Yes. There's a software called I'm forgetting the name. It is Storm, Spark, all of these. They have libraries in order to enable all of these. They can support the Lambda architecture, and they can also support the windowing techniques like this, whether it's landmark or whatever. So using all of that, you can actually build this type of whatever you're talking about, and they are into practice. But they do not share, because that is in trade, in the stock market trade, that is actual money. So don't share the algorithms.
I now request our student Arindam to present a memento to Mr. Sumit Misra as gratitude for his presence and very interesting talk. So we have